our topic is all about the RLC circuit. RLC circuit consists of resistor, inductor, and a capacitor in parallel or series with a battery. RLC circuits are mainly used as oscillator circuits in some applications. In radio and televisions, they are called tuning circuits.
Okay, so for today we're going to tackle about RLC circuits in series. They are all connected through one wire. So how do we apply differential equations in RLC circuits? First, we have to know some of the formulas for in electrical circuits, such as Kirchhoff's law and other formulas for capacitance and inductance. So for first, we know that through Ohm's law, Kirchhoff's law, voltage is equal to IR. So that's the voltage across the resistor. So we're gonna write that here. And the current that's going to the inductor would be L di over dt. That is the common formula used for inductors and inductance. And for capacitance, which is denoted by C, formula is 1 over C integral of 0 to t of of the current. So these are all the applications, the formulas, so that we can find our differential equation for our series RLC circuits. So to better understand this form of the equation, we should differentiate each of these functions. So here, if we differentiate this with respect to the current, R is di over dt, plus we differentiate this, which is equal to d squared I over dt squared L. And for the capacitance, the integral sign will be removed, so it's going to be I over C. We differentiated them so that we can get rid of the integration sign, and which helps us to make the equation easier to understand. And from here, we can divide all sides by L, rewriting the equation whilst dividing by L. This would be our differential equation for series RLC circuits. D squared I plus R over L di dt plus 1 over LC I equals 0, wherein L is the inductance or the inductor, R is the resistance, and C is the capacitance.
Okay, for our sample problem, a series circuit has a capacitor of 10 raised to negative 5 farad, a resistor at 8 times 10 raised to 2 ohms, and an inductor of 0.2 Henry. Initial charge is 10 raised to negative 6 coulombs and no initial current. Find charge Q on the capacitor at any time t. Okay. How to solve this problem? First, let's identify the givens: the resistance, inductance, and the capacitance. The resistance is the 300 ohms. The inductance is the 0.2 Henry. And the capacitance is the 10 raised to negative 5 farad. The Q Q of 0 is 10 raised to negative 6 coulombs, and Q prime of 0 is 0 amperes. Okay, in order to solve this problem, we have a formula of LQ double prime plus RQ prime plus 1 over CQ equals to 0. This formula came from the general formula of RLC circuits in series. This formula, also known as the second order differential equations. Okay, let's put the values in the formula. L is 0.2 Henry double prime plus the resistance is 300 ohms Q prime, and the capacitance is 1 over 10 raised to negative 5. 10 raised to negative 5 Q is equal to 0. Okay. Let's divide both sides by 0.2. 0.2 H. 0.2 H. To simplify, it is Q double prime plus 300 divided by 0.2 is 1,500 Q prime plus 500,000 Q by Q is equal to 0, and R squared plus 1,500 R plus 500,000 goes to 0. Okay, let's find the roots. In order to get the roots, we will use the quadratic formula. The formula is R is equal to negative 1,400 plus and minus 1,500 squared. Minus 4 times 1, 500,000 The roots are negative 1,000 and negative 500.
Okay, so now that we have our roots, which is based from our formula of the which is the second order non-homogeneous differential equation, the roots are negative 1,000 and negative 500, and now we can now get our characteristic equation, or Q of t, which is Q of t equals to C1 E our root negative 1,000 C plus C2 E negative 500 T. And this would be our characteristic equation, which we are going to solve for. And based from our given, we have a given of initial charge, which is 10 raised to negative 6. Coulombs. And given that we don't have any initial current, Q prime of 0 is equal to 0 amps. And based from this, these given, we now know that we have to solve for the initial value problem. Solve IVD. Now we just substitute, take the differential of this. So once we differentiate this equation, the characteristic equation, it will be negative 1000 C1 E raised to negative 1000 T plus C2 minus 500 C2 E raised to negative 500 E. So this is the differentiation of the characteristic equation. Now we substitute in our initial values into the characteristic equation and its differential based on this. So we sub this to the characteristic equation and 0 to the differentiation of the characteristic equation. So Q of 0 is equal to 1 plus C2 equals 10 raised to negative 6. Because we know Q is equal to 10 raised to negative 6, and we substitute 0 for T, so this will cancel, and substituting 0 here will also cancel, so we're left with C1 plus C2 equals to 10 raised to negative 6. And for Q prime of 0 is equal to negative 1000 C1 minus 500 C2 equal to 0. It's equal to 0 because the given is Q for Q prime is 0 amps, and substituting 0 for the differential, which is, will cancel the E, the exponential, leaving us with negative 1000 C1 minus 500 C2. And now we can equate this with this equation, and this is the second equation. Now we can solve this system of equations either using by matrices or just solving by substitution or whatever. So once we find the answers for C1 and C2, the values would be negative 1 times 10 raised to negative 6 and C2 would be 2 times 10 raised to negative 6. So the charge at any time t is qt. Substitute this into the characteristic equation, so it would be negative 1 times 10 raised to negative 6 e negative 1000 plus 2 times 10 raised to negative 6 e negative 500 t coulombs. So this is our final answer for the Q charge at any time t. So from there we can substitute any time in seconds here and here, so we can figure out the value of the charge across the capacitor.
In a series RLC circuit at resonance, the current is limited only by the resistance of the circuit. I is equal to V over R. If R is small, consisting only of the inductor winding, then this current will be large. It will drop a voltage across the inductor of an equal magnitude voltage will also be seen across the capacitor, but in an anti-phase to the inductor. R can be made sufficiently small, these voltages can be several times the input voltage. The voltage ratio is in the back of Q of the circuit. A similar effect is observed with currents in the parallel circuit. Even though the circuit appears as high impedance with the external source, there is a large current circulating in the internal loop of the parallel inductor and capacitor. This is an application of the RLC circuit, which is also called voltage multiplier.